also the other important point I'm going to study also as part of the view and also for the first midterm is the graph theory, and we started the representation of graphs. So we have vertices and edges. Vertices are those guys, nodes, sometimes called nodes, and the edges are the lines connecting them, right? And a graph is represented by the set of the vertices and the set of the edges. The edges are represented typically by the two vertices that are connected to that edge. So this is edge 1, this is edge 2, this is edge 3 that you see here. The graph can be undirected like the one you see here, so there are no arrows, so this connection goes both ways, or it can be directed where the connection can go in a certain predefined direction. And you should be able to deal with both the directed and the undirected graphs. This is just a set of terminologies. One important thing about graphs is a property of the vertices called the degree. And for the undirected graph, the degree of a vertex is the number of edges connected to that vertex. For directed graph, there is in degree and out degree. So the in degree, the number of edges going into the vertex. The out degree is the number of edges going out of the edge, out of the vertex. Okay, so we have two types. The total degree is defined by both the in and the out degree. Okay, we have a few theorems. So the first one says that it's called the handshaking theorem, and it says that number of edges multiplied by 2 is equal to the sum of the degrees of all the vertices of a graph. And that's true for any graph, for any undirected graph. Okay? The other theorem, also for undirected graphs, says that in any undirected graph, there is an even number of vertices that have odd degrees. So the sum, the total number of vertices, which are each with odd degrees, that total number of vertices is an even number. Okay. The third theorem that we have was actually for directed graph, and in that one we say that the sum of the input degrees or the end degrees of all vertices equals the sum of the out degrees of all vertices, and that is equal to the number of edges. So that's the theorem for directed graph. The sum of in degrees, out degrees equals to the sum of n degrees, and the sum of n degrees equals sum of out degrees, and that is equal to the total number of edges in a directed graph. Some important definitions. What's a complete graph? A complete graph is a graph where each vertex has an edge to every other vertex. So any vertex is connected directly to another vertex using a single edge, and given the symbol capital K, and it has a degree, which is the total number of vertices. So this is K3 because it has three complete. A graph with three vertices. K4 is complete graph with 4 and so on. Another thing is what's called a cycle. A cycle is where you can move in a fully closed circle, passing each each vertex in the graph through a single edge. And you see here an example of cycle of degree 3, cycle of degree 4, and it's given in capital letter C. Also, there's something called a wheel, which is a cycle with a central point that is connected to all the others. So a W4, a cycle of degree 4, is a cycle with 4 vertices, right, added to it, and one more vertex connected to all the other 4 vertices. That's called a cycle of degree 4. Notice that here we say degree 4 even though it has 5 vertices, because the cycle generates from the wheel generates a wheel, right? Generates from a cycle, and then we add one more vertex. Okay, that's why the degree here is actually the degree of the cycle that generates the wheel. Okay. Bipartite graph is a graph where you can divide the vertices into 2 separate sets, such that each set does not have edges between the vertices inside that set. and the only existing edges are connecting between vertices in the two different sets or groups. Okay, so this is an example of a bipartite graph. If every single edge here, sorry, vertex here is connected to every single vertex here, a complete bipartite graph. Okay, and next, a subgraph of a graph is a subset, it's composed of a subset of the vertices and the edges. And you can do a union of subgraphs so that you can construct a super graph of those. Okay? That's the case. Then there are two ways to represent graphs, either using the incidence matrix or the adjacency matrix. The incidence matrix is the representation. We have it here, where we have on the columns are the different edges, and then the vertices are the different rows, right? So here, and we have the columns labeled by the edges that we see here. And then we have a 1 whenever the edge is connected to the vertex. So E1 is connected to V, so we have a 1 here. E1 is not connected, that edge is not connected to W. So this is why with E1 and W, we have a 0. This is an incidence matrix. Representation is the adjacency matrix. In this case, it's vertices, and then we start. Vertex V and U, if they are connected, so V and U are connected by an edge, we have a 1. V and W, they are connected by an edge, they have a 1, right? V to itself, V and V, no, there's no cycle here, there's no loop here, sorry. So 0, okay, and so on. So that's the adjacency matrix. Should be able to do, if you are given a graph, you should be able to do the incidence and the adjacency matrix if you are asked to. And also you can be given the incidence of the adjacency matrix and asked to draw the graph using vertices and edges. You should also be able to do that, okay? Isomorphism is another important concept, that two graphs are isomorphic of each other, which means that they are equivalent to each other if we can map them. And as we see here, for example, we have U1 connected to U2, connected to U4, connected to U3, and we can see that I have V1 connected to V4, connected to V2, connected to V3. So this graph is equivalent to this graph with only one thing that I would consider U1 equivalent to V1, U2 is equivalent to V4, right? Because it's the one connected to that, it's the one connected to that. And then U4 is equivalent to V2, right? And then U3 is equivalent to V3. And if you do that equivalence, you can see that these graphs are exactly the same. You can also see that they are the same if you think that you have moved this down here, right? So it will become a square similar to this one. Anyways, another important concept in graphs. In a graph, reachability among vertices means that you can go from one vertex across multiple edges until you reach the other vertex. In this case, you say that vertex B is reachable from vertex A. Okay, and then as part of the connectivity, you have something called a path, a sequence of edges that begins at a vertex of a graph and travels along edges of the graph, always connecting pairs of adjacent vertices. So, for example, this is a path, right? U145V. This is a path U1432, and so on. Now, question is, in this graph, right? Every single vertex is reachable from every other vertex. Then this graph is connected, which means that you can reach any vertex from the other going through the available edges there, right? So you can go from 5 to 2 by taking this path. You can go from V to 1 by taking this path, and so on. Okay? Okay, so that's a path. A cycle is where you start at some vertex, you go across the edges, and you manage to get back to that same vertex again. That's called a cycle. You have a path, you start at some point, you finish at another point, and all the time you are going through edges. You're not just flying, so you cannot do this, for example. Okay? You have to go with connected available connected edges. And if it is directed, you have to also abide by the direction. Okay, that's a path. A cycle is you start, you move across edges, and you manage to come back to the same. That's called a cycle. Okay? In an undirected graph is connected. We call a graph connected. I mentioned that already in the previous slide. If there is a path, a simple path that starts at one vertex and can reach the other vertex between any two vertices. So I can reach anyone from anyone going through the path. This is called a connected graph. For directed graph, there is strong connectivity, weak connectivity, right? Strong connectivity means by abiding between two vertices means that you abide by the directivity of the edges and you can reach vertex B from vertex A. The weakly means that there are edges, but the directions does not allow you. So if you assume that they are undirected, you could actually reach B from A. But when you consider directivity, you cannot. Okay, so that's called weakly connected. If there is none, even if you ignore the directions, then they are not connected at all, neither weakly nor strongly. Okay? So here, for example, for this directed graph, it's weakly. This one is strongly connected because from any vertex you can reach all the others. If you start at any one, you can reach all the others. Right? For this one, if you start here, you can reach this, you can reach this. If you start here, you can reach this, you cannot reach this, right? You cannot. Even going this way, it doesn't. So this is weakly connected. Okay? This is weakly connected. Because if you start anywhere, you cannot reach the others, but if you ignore the directions, then you see that you can reach all the others. Another important theorem is if you have a graph with adjacency matrix A with directed or undirected edges. Okay, the number of different paths of length R from vertex VI to vertex VJ, where R is a positive integer, equals the IJ element, so the element of row number I and column number J of the adjacency matrix A of the graph raised to the power R, which is the length. Length of a path means the number of edges that the path contains. Okay? And we have solved a problem like that. No need for proofs, as I mentioned already. This we should be able to use a theorem if you need to calculate paths. And also sometimes I might ask you to point out these paths, as we did in this example in the lecture. Also, be careful to be okay. Important properties or types of graphs, the Euler and the Hamiltonian. So an Euler path and an Euler cycle. So an Euler path is a path that manages to go across all the edges of a graph only one time without missing any of the edges. Okay, and without going over any one of them more than once. That's called an Euler path. And a graph is a path that uses each edge precisely once. If such path exists, then the graph is called traversable. And if you manage to do the same like this, but you actually start and finish at the same vertex, then in this case, you have something called an Euler cycle, and the graph is called Eulerian. Not traversable, but Eulerian. So you manage to go over each edge once, and you end at the same vertex that you started from, and that's called an Euler cycle or Eulerian cycle. Okay, there are two theorems about that, and they are if and only if theorems. So if the theorem is true, the the property is true. If the theorem is wrong, the property is wrong. It is Eulerian if, and it is not Eulerian if not. Same thing for theorem two. You should be able also to understand and use these theorems. For the Hamiltonian case, we look at the vertices. We are not caring about the edges. And a Hamiltonian path is a path that goes across each vertex only once. Um, and it starts and finishes at two different vertices. A Hamiltonian cycle is a cycle that starts at the vertex and finishes at the same vertex, going across all the other vertices only once, except the one that you started from, because in that case, it goes twice at the start and at the end to form a cycle. Okay? And again, there are a couple of related to the Hamiltonian, but those theorems are not if and only if. You have to be careful when you use them. I've already elaborated on that in the lecture. Please understand how to use those theorems. Both of them actually talks about Hamiltonian circuits. They are not related to the Hamiltonian path. Okay? But again, always when you have a Hamiltonian circuit, you will be able to have a Hamiltonian path, right? Because if you imagine, if I start at some particular, right, maybe this is how my Hamiltonian circuit path is, and if it's complete. I'm sorry, this is my how my Hamiltonian circuit is. If I start at one, I go this way, right, this way, this way. I finish the cycle. I can always go this, 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 and stop here, right, without going across the last edge, and that's a Hamiltonian path. So whenever I have a cycle, I can always reduce it to a path. If I have a Hamiltonian circuit or cycle, then definitely I also have a Hamiltonian path. The other way is not correct. I might have a path, but maybe these two are not connected, so I will never be able to have a cycle out of that. Okay? That's one important thing. Last thing was the shortest path problem. The most important part in that you can actually how the Dijkstra algorithm works on a particular step by step as required. I might ask you to do it between start and an end node, or from a start to all the other nodes, or maybe a couple of steps, not until you find the shortest path. Show me the first two steps and the first three steps and so on. But you should do that, and I remind you, you have to do this step by step, showing in every step what happens, similar to what you have. And thank you. That's it. Please prepare. Good luck with your midterm. Be ready. And I wish you the best.